Do you find it hard to believe that we can make a microscope from a Blu-ray player? Well, in my last two videos I showed how the optical pickup unit can measure distances very accurately, up to the point where it can even act like a microphone. In part 2 I modified the mechanics a bit, so the laser scans the object from left to right while a stepper motor pulls it from top to bottom. Meanwhile, the sensed amount of reflected light was digitized and displayed on an HTML site, so creating the visual representation of the object being scanned. However, this construction was far from perfect for mainly two reasons. Firstly, the follower on the lead screw sometimes skipped a step. Secondly, the pitch was quite high, so I couldn't achieve a better resolution. What's more obvious than using a different motor with a finer lead screw? This didn't, however, fit into the construction I already had. So I designed my own mechanics around it with FreeCAD. After I finished that, the sponsor of this video, PCBWay, came in. PCBWay not only makes circuit board, but it also offers manufacturing services like CNC machining, 3D printing, sheet metal fabrication and injection molding. So I uploaded my CAD files to their website. Then I had the choice between a whole lot of materials, from resin to titanium. There is a description of the selected material below, which helped me to find the right one for my project. So I decided for the UTR 8360 resin, which has all properties I need and which is also cost effective. After a quick online check of how the parts would turn out and another thorough review by PCBWay overnight, I finally placed my order. And a few days later, a packet from China arrived. Let's open it up and see what's inside. It's the 3 items I ordered. They arrived safely and well protected. I'm carefully unwrapping them and the tension rises. Wow, look at this quality! Feels so perfect and classy. Finally I unwrap the last part. And there we go. So I put them together. First I mounted the stepper motor. To do this I first had to drill a hole for the fixing screws. If I had known their exact positions during the design phase, I would have designed them in CAD, but the drilling was done quickly anyway. Next I placed the object sled on top of the lead screw so that the brass nut fits into the recess. Here I put in 2 stainless steel rods as tracks for the sled. They come from the defective Blu-ray player I disassembled for this project. Such rods can of course also be bought at any hardware store. To fix these, I put 2 M3 nuts into the recesses and turn in 2 screws. There we go. The optical pickup unit gets loosely mounted between 2 threaded rods. This allows for shifting it from left to right to position it precisely above the specimen. It can be flipped open, making it easy to access the probe. Now I assemble this on top of the base with bolts, thumb screws and 4 springs in between. At the end, the springs and thumb screws hold it in place. This allows for a coarse adjustment of the distance between the pickup unit and the sample. That's all about the mechanics. A simple and straightforward construction, isn't it? But we also need some electronics though. I soldered all that's needed on a prototype board. Then I connected the pickup with a 40-pin ribbon cable plus adapter. And plugged in a 4-pin connector for the stepper motor. And now I'm gonna tell you how it works. This transistor pair controls the current that flows through the laser diode. Next to these, there is an LM7805 5V regulator and 4 op-amps that amplify the sensor signals from the pickup. So they represent the amount of reflected laser light as you can see on the LED. Then we have an L293 half-bridge driver IC for the deflection and focus coils. And finally an STS pin 220 stepper motor driver module for the motor that drives the object sled. And ESP32 controls all of this stuff and also hosts a web-based application that allows us to operate the microscope over Wi-Fi and through a web browser. Alright, let's check out the website then. In the middle there's a canvas where the images appear. On the left there are controls for brightness and contrast. And on the right we can set resolution, scan speed and other parameters. And of course, start the scan. Down below we can see the connection status of the ESP, an indicator for the reflected light, and two buttons that let us manually adjust the object sled's position. Okay, now let's test it. But first I need to do some adjustments. I fine-tuned the reference voltage of the op amps by turning the trimmer, so that the indicator shows a minimum value. It's also important to set the right current for the stepper motor. Too little power results in insufficient torque for moving the sled. Too much power causes overheating and can damage the motor. To find the right setting, I move the sled with the arrow keys on the website and adjust the trim pot on the driver module until the sled moves smoothly. Applying a droplet of oil to the tracks and lead screw helps to reduce friction, and as a result reduces the amount of current required. Then I place a microscope slide in the recess of the object sled and put a piece of paper on top. Then flip the pickup down and turn the knurled knobs until the LED lights up. Now we have the right distance between the pickup lens and the probe. Ideally, the top and bottom pieces should be about the same distance apart on each edge. Okay, the microscope is now ready for use. Let's figure out how to operate it and see how it performs. I've got a calibration slide for microscopes placed on the object sled. This has small engraved test patterns and I'm gonna test my microscope with the one with the circle around. As the pickup is loosely mounted between the two rods, I can easily move it from side to side. And the two buttons on the website let me drive it up and down. So by viewing the sample from above through the lens, I can accurately target it that way. Back to the website. With the laser at maximum power, I move the focus slider until the indicator at the bottom reaches its maximum. Then I take the laser power back a bit and search for a maximum with the fine focus control. Doing so brings the sample exactly into the focus of the laser. There we are. Then I click the scan button to start the process. There comes a grey horizontal bar and some vertical lines. Now the calibration pattern is formed. Let's count these longer vertical lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. These lines are 0.1 mm apart, so the scan area is 0.9 by 0.9 mm. There's another control labeled scan speed, so let's make it faster. As you can see, the horizontal line is starting to fray. And that's because the scan head is controlled by a PWM signal coming from the ESP32. This means that it jumps from one scan point to the next, and these jumps make it wobble for a while. And that leads to these frays. With a delay of a few hundred microseconds between each jump and the following measurement, the scan head can settle and the frays are gone. You may also have noticed that the image looks a bit grainy. That's because of noise. I can select here whether to scan every point 1, 4, 8 or 12 times and make the average of these values. You see that the noise has become less, but scanning runs also slower now. The low resolutions are useful to quickly check the positioning of the sample. This first scan looks promising, so we can switch to a higher resolution and start over again. 240 by 240 is twice as much as the previous 120 by 120. So it now has to scan twice as many points per line and twice as many lines as before. This makes the scan take 4 times longer. But with a time lapse of 7 you don't get bored. But the waiting is worth it. We can already make out much more details now. Let's try 480 by 480. Now the time lapse is 20. That looks decent, doesn't it? I turn up the contrast a bit. Nice. We can clearly see the lines now. Here's a shot I took with the highest resolution of 960 by 960. It took about 20 minutes to finish. To speed things up a bit, I scanned at full speed at the beginning. When it got to the more interesting parts in the middle, I slowed down. We can clearly see the differences in quality. But we also see the shortcomings. The horizontal lines look quite washed out. I have no clue why. Maybe you have an idea? Then post it in the comments. And there's also blurring and artifacts at the beginning and the middle of each line. I suspect that the PWM signal from the ESP32 is inaccurate at these points and thus causes these glitches. But apart from that, the microscope works quite well. The distance between two lines is 10 micrometers. I estimate that such a single line might be 2 micrometers wide. So with the highest resolution setting we scan an area of 0.9 by 0.9 millimeters with 960 by 960 dots. This gives us a theoretical resolution of 937.5 nanometers. Good optical microscopes, however, reach a resolution of up to 200 nanometers. And they cost a fortune. Of course you can't expect miracles from such a low budget toy, but it was still fun to build it. For sure I can still try to improve the resolution even more. The STS-220 driver module can achieve 256 microsteps, which results in a resolution of about 100 nanometers. However, I need to increase the current through the motor even more to achieve this. This makes it so hot that I'm afraid it will burn out. And the thing will become even lamer than it is anyway. Taking a 480 by 480 picture in good quality already takes around 5 minutes. In any case, there is always a trade-off between resolution, image quality and scan speed. The other constraint is the accuracy with which the pickup lens can focus the laser. This is of course limited by its wavelength of 405 nanometers and also depends on other factors. So that's the strongest limitation. This image shows that the spot of a Blu-ray player has a diameter of about 480 nanometers. So it won't accidentally touch the neighboring tracks. And that's the best resolution we can get. It's 2 times higher than the 900 something we've already achieved. Now let's compare 2 shots I took. One is 480 by 480, the other is 960 by 960. Both scaled up to the same size. The 960 by 960 image is a bit sharper, but I waited half an hour for it to finish. The motor got hot as hell and already started to stink. For finer resolutions I will definitely need to use a stepper motor with higher power rating, like this NEMA 17 motor. I will leave it as it is and come to the end for now. Thank you for watching and see you next time.